Okay, questions? Sarah?
B on the backside.
B on the back side. That one, right?
Yeah.
Okay. Okay, so if you're, whenever we have a carbonyl with a potential leaving group, which was the esters and acid chlorides here, we're going to have the Grignard come in and add to the carbonyl so that we're going to have one of the Grignard groups add, so we end up with this alkoxide. And then we said that alkoxide is going to try and do what? It's going to try and reform the double bond, so this pair of electrons can move down and reform the double bond if there's a leaving group attached to that carbon, which is what the chlorine is. So it could then kick off the chlorine so that we lose Cl minus, and now we've made a ketone. The problem here being that once I make the ketone, I'm now going to add a second equivalent of Grignard to that ketone so that the final alkoxide is going to have two of the same Grignard groups added to the carbonyl. So at this point, if the O minus tries to bring its pair of electrons back down, nothing can leave. So it's stuck. So then what's going to happen is then we're going to add our H plus H2O step, and we're simply going to protonate the O minus. Now, somebody asked earlier, they said, well, what about the H plus H2O adding to the double bond? And that's something that we would worry about if we were going to really do the lab. So for instance, if I was adding H plus H2O to this alkoxide and I was concerned about reacting this double bond, I certainly probably would not use HCl, HBr, or even sulfuric acid as my source of H plus. The intent here of the then H plus H2O step is simply to make the OH. I personally might say, okay, you know what? I'm going to use an ammonium ion as my source of H plus, because it's going to be a relatively weaker acid than HCl or HBr or sulfuric. So that way I would just protonate and not add any acid to the double bond. But whenever we whenever we add a Grignard to an acid chloride or an ester, we always add two and then end up with a product with both of those groups then added to the carbon. In this case, a tertiary alcohol.
Can we do B on the front side?
Okay, so B on the front side. We're going to talk about the mechanism of that in a couple months. But here's what happens when you use lithium aluminum hydride with the alcohol, or sorry, with the carboxylic acid. In your oxidation reduction scheme of primary alcohol if you take a primary alcohol and you oxidize it, you first form an aldehyde, which then you can oxidize again to form the carboxylic acid. In terms of reductions then, so an O in brackets means oxidation, which is the topic for Wednesday, is oxidation of alcohols. But if I now reverse this, I could go from carboxylic acid to aldehyde, and the lowest in this scheme is the alcohol, primary alcohol. So what happens is when we add lithium aluminum hydride to it, we're going to reduce the carboxylic acid all the way down to a primary alcohol. That's what the lithium aluminum hydride does. And there's two, so lithium aluminum hydride is a source of H-. Sodium borohydride is also a source of H-. It is a reducing reagent, but it's not strong enough to reduce a carboxylic acid. So you've got to use lithium aluminum hydride, and it'll take the carboxylic acid all the way down. It would take an aldehyde down to a primary alcohol as well. So the mechanism of that we'll get to, but not today. So the lithium aluminum hydride is interchangeable with sodium borohydride. I mean, it'll do everything that sodium borohydride will do, but sodium borohydride will not do everything that lithium aluminum hydride. So when you're reducing a carboxylic acid, it's got to be lithium aluminum hydride. You don't have a choice. It's got to be that. That's a fairly potent reagent. I said last time somebody used it in my lab, they caught it on fire. That was over 20 years ago, and I was a graduate student when chemistry had graduate students. All I know is I came back to the lab and he goes, "Yeah, that lithium aluminum hydride bottle, it caught on fire." And I said, "Okay, how'd you put it out?" And he goes, "I just pour sand on it," which was the correct call. Because if you poured water on it, then it would react with the H- and form hydrogen gas, which would make the fire even worse. But this was a graduate student that worked in industry, so he wasn't fazed by it. If he wasn't fazed by it, I wasn't fazed by it. Except next time you use it, be careful. They keep a bottle of sand next to it. So that's the oxidation reduction scheme for primaries, up to carboxylic acids and back down again. What else?
Can you go over C? Same time.
So that one we can actually talk a little bit about the mechanism of. So if we have an ester, because the biggest problem with the ester is it splits apart. The carboxylic acid didn't really split apart, although it did. So if we think about the lithium aluminum hydride being a source of H-, what's the H- going to do with the ester? How's it going to react? Josh?
Is it going to remove the OCH2CH3 and also cause it to form primary alcohol?
Yes, but in terms of the mechanism, what's the first step in this mechanism? The H- is going to do what? Attack the carbonyl. Attack the carbonyl carbon. Is that what you were going to say?
Yeah.
So we're going to have the H- attack the carbonyl carbon. Where have we seen that before? R minus. So R minus, H minus, all going to do the same thing. Attack the carbonyl, make the alkoxide. What's going to happen next?
I was going to try and make itself move again.
Well, carbonyl. And then what happens? Go ahead, it's your question.
I'm just going to break off the OC.
So the OCH2CH3 is going to leave as a leaving group. And so I'm going to end up forming then, in this case it's not a ketone, it's an aldehyde. Plus then I would make my OCH2CH3 minus. Then what is, so the thing with lithium aluminum hydride is it has 4 H minuses that it can give up. So then the second equivalent of H minus comes in, adds form an O minus. Can the molecule reform the carbonyl? Not without something leaving. There's nothing there that's going to leave, and so it just kind of hangs out. And then when I add my H plus H2O step, the H plus is not only going to protonate the alkoxide, it's going to protonate the other alkoxide. So in this case, the final products are that this part of the ester is going to form a primary alcohol, and the alcohol part of the ester is going to split away and form. I don't think we're at, maybe in the next, by Friday, what we're going to find out is that if I wanted to take an alcohol and make an ester out of it, what I would do is react the alcohol and the carboxylic acid to make the ester and water, and I just need acid as my catalyst. So when we make an ester, we think about the ester form. This came from the carboxylic acid part, and this part came from the alcohol. Right, and we'd have to go back if you were with me last semester, we'd have to go all the way back to naming to talk about the alcohol part of the ester and the carboxylic acid part of the ester. But we're going to get to this reaction because we're going to do reactions of alcohols soon. So when you cleave an ester, the carboxylic acid part becomes a primary alcohol, and then the alcohol part gets split up and just becomes an alcohol. But the reason why it splits is because of that mechanism. So that mechanism is exactly the same for H minus as it is for R minus.
I just had a question. Before the exam, are we going to get a list of all the mechanisms to make sure we don't have any, like, missed in our notes or something like that?
Missed in your notes.
Just so you, like, make sure you know all the mechanisms.
I would make sure I know all the mechanisms before the test.
I know, so we'll have, like, a list of it on campus?
Maybe. But here's what I am doing. I am putting these notes on Canvas. But I don't know if I missed any or not. So that's where the book is important. And the other notes of the video. And at the end of the chapter, they should have all the reactions that you do in the chapter as a summary. And then you have all the old exams. And the probability may just pull in a random reaction from wherever I pull it from. It gets slimmer and slimmer every year. There's only so much creativity I can show. I'll still put a different kind of problem on there, and people will still say, where did you pull that out of? And I'll be like, I don't know, because you got 10 years worth of exams. So I could do that, but you know what would be even more effective? If you did that. So just keep track of them every day. What else?
Can you add on the same side?
Okay. So we now have two ways to do this problem. So we have two ways to do this problem. We could write the mechanism out, or we could remember how to split up the molecule. So how would I split the molecule? How about like that? So what's the group on the left become?
Primary.
Becomes the primary alcohol. So that means I'm going to take my C double bond O and I'm going to make a CH2OH out of it. So there's the primary alcohol of the part on the left. What happens to the part on the right? It just becomes the alcohol that it is. In this case, a secondary alcohol. So all I do is split it apart and add an H to the O. So those are going to be my two products.
If the secondary alcohol starts off as an O minus, how does a reducing agent cause it to, or is that where the H plus comes in?
So when we split it apart, we form this, right?
Yeah.
So then that stays as an O minus until I add H plus H2O to it.
Okay.
So let's say if you were in the lab, what you would do is you'd add acid to it and stir it around until the solution became overall acidic. Right? And so you'd use the pH test paper and you keep testing it until it was red. So you'd have to add more acid because not only would I have to protonate this alkoxide, but I've got to protonate that one as well. But in the end, they both would become an alcohol as they're being, as they're reacting with acid. So they would get changed over in the N, then H plus H2O step.
An H minus won't react with an O minus to form an alcohol or form water.
Well, let's think about that. So an H minus is what? What is an H minus? And a base. What's alkoxide? A base. So there's no acid there for the reaction. Bases don't react with bases. Acids don't react with acids. You have to have one of each. So in that case, the H minus isn't going to touch the alkoxide. It's just going to wait to be deprotonated or wait to be protonated. All right. What else? Well, that's what the timing is about, because in all these reactions, there's a then H plus H2O step. If I added the acid while the lithium aluminum hydride was there, I would kill the H minus. And so that wouldn't be able to be reduced. If I added the acid while the Grignard was present, I'd kill the Grignard. So after the reaction's over, then you add the H plus H2O step. So it's been really a two-step process. What else? What about the reactions of oxides with Grignards? So I have my generic Grignard, and I'm going to react it with this epoxide. And so I've got my two carbons A and B on that epoxide. So where's the R minus going to add? Okay. Do we all agree with that? So the Grignard's going to react with carbon B because it's least sterically hindered, and then it's going to open up the epoxide that way so that the OH is going to be next to the ring and the R group will have added to the other carbon. But I have a question. So A, what kind of carbon is A? Primary, secondary, tertiary? Secondary, what kind of carbon's B? Secondary. They're both secondary.
Wouldn't A be a tertiary? Because, why not? Oh no, never mind.
All right. The difference between lying and being mistaken. In court, if you are mistaken, it just means you made a mistake. If, on the other hand, your answer is intended to deceive me, you are lying. So I don't think you were lying, I think you were just mistaken. So if somebody accuses you of lying, there has to be intent to deceive them. A simple mistake is a simple mistake. Or a big mistake, but still a mistake if there was no intention. Every so often I have to go through the difference between that. Because people come up and laugh, oh, I lied, I only weighed out like 0.5. Well, again, intent. So now it's still secondary. Does that play a role, the fact that they're both secondary? Well, they're tied, basically, right? If they're both secondary. So then you got to look at the group. So a cyclohexyl group is bigger than a methyl. So that's the steric hindrance. If I had a secondary versus a primary, it would go to the primary. So we've got to look at the steric hindrance both in primary, secondary, tertiary terms, but also then in terms of size of group terms. So with the methyl group being smaller than the cyclohexyl, the R minus will definitely add to the carbon B. So then the question becomes, well, why is that? Why is it that the Grignard is going to react with carbon B and not carbon A?
Is it just physically better? What is it?
Yeah, but what if I did this? What if I did this first? And I said, you know what, I'm not going to add R minus, but maybe I wanted to add an OR. So I'll add I'll add acid and alcohol to this epoxide. I'm going to open it up. I'm going to end up with an epoxide, or with an OH on one side and an OR on the other. So is it going to look like this, or is it going to look like that? So in other words, of carbon A and B, where's the OR group going to end up? On A or on B? A? How many people say A? B? Both. Meaning that it'll be a mixture of the two products. Any other answers? No reaction? That's going to react. Okay. So what we need to do is we need to compare and contrast these two reactions. One, where basically I'm going to redefine the term and say we add strong nucleophile to an epoxide, and the other one is going to be under acidic conditions. Sometimes this is called acid catalyzed cleavage, and then basic cleavage is certainly not base catalyzed cleavage. But these are two different reactions potential, or there's two different reactions, strong nucleophile or with acid. So where's the alcohol going to add? Okay. So we need to talk about the bottom reaction. And let me make it a little clearer. Let me put two methyl groups here. Okay, I'm going to add H plus to this epoxide. What should I do? What's the first step going to be? Protonate what? Protonate the oxygen. So whenever we have an oxygen-containing compound and we add H plus to it, what should we do? Protonate the oxygen. Okay. I've said that probably more than 20 times this year, which is okay because that's what you do. Protonate the oxygen. Okay, so I'm going to protonate the oxygen. And form a plus charge. I'll take the approach that I used this morning and ask a series of questions. It's more fun if we randomly ask people. I know it stresses you out, but that's okay. This is a 50-50.
Sam Heaton.
So here's my question. Keeps everybody on their toes. Here's my question, Sam. Is that oxygen happy with that positive charge?
No.
No, why not? Do you need help?
Yeah.
Why is the oxygen unhappy with the H+?
Zach Twinotics.
Because it's more electronegative.
It's an electronegative element. So it does not want the positive charge. So what is it going to do? No. Short of rearranging, short of breaking a bond, what's it going to do? Did you have your hand up, Kevin? Can't leave. Short of breaking the bond. What's that oxygen going to do with its positive charge? Share it with carbon. How about A and B? That's both, yes. So the oxygen is going to push its electron density off to the carbon. Because the carbon at least can take a positive charge, we know. Okay? So we protonated the oxygen. It pushed its electron density down to these two carbons. And they are going to be delta plus each. But for the most part, they're going to share a positive 1 charge overall. So my next question is going to be, Kevin, which carbon of A and B is going to have the greatest delta positive charge?
Should be the. It should be B. Because it has. Because it's got 3 actually where the other one is too.
So it's tertiary. Exactly right. So this B is going to have a greater delta positive charge. Why? Because looking at C, it's a tertiary carbon versus looking at A, it's a secondary carbon. Now, if I did break the bonds, then if I broke the bond and put the OH on carbon A, it would be a tertiary carbocation fully. If I broke the carbon A oxygen bond, then it would be a secondary carbon. And which one of those is going to be more stable? The tertiary one. Okay. So, but I don't break the bond completely. Because here's what I know. I know when I add the alcohol now to that molecule, the OH and the alcohol will be trans. If the bond was to break, I'd end up with a tertiary carbocation that the alcohol would add 50-50 to both sides. So I know the triangle stays intact because I get 100% trans addition. Okay. So then this is going to come in, add to carbon B, break the bond of the carbon B OH group, and I'm going to end up with I'm going to end up with an oxonium ion, right? And then that oxonium ion is going to lose its H plus to make the final product, where the final product will have the OH and now the OR a 100% trans. So does everybody kind of see the logic here? When an acid is present, it will always protonate the oxygen. When it protonates the oxygen, that will push the positive charge into the 2 carbons of the epoxide. If one of them is more able to take on the charge, it will. And then where will the alcohol add? The alcohol will add to the carbon with the greatest positive charge, which is also going to be the carbon that is most substituted.
So if they were both secondary, then would it be mixture?
Yes. Yes, it would be a mixture. And I'll come back to that because you might want to make an argument that is incorrect. But after my next question, maybe it'll become a little bit clearer. So what's my next question?
Dylan Ramsey.
So Dylan, here's my next question. What kind of reaction does this remind you of? SN1 or SN2?
SN1.
SN1? Do we agree with that? No? You think it's SN2? Anybody think it's SN2? Why do you think it's SN2?
Because it's like having the multiple steps. Like the triangle and then the HOR adding.
They're doing backside attack?
Yeah.
So there is that SN2 characteristic of the backside attack. But what drives, what's the difference between SN1 and SN2 in terms of what makes the reactions go faster? So in SN1, how do you make a reaction go faster? What's the rate of the reaction dependent on? What? SN1. How stable the carbocation is for SN1. How do you make the reaction go faster? Make a more stable carbocation. I could go into the gory details, right? What's the rate determining step of an SN1 reaction? The formation of the carbocation. If the carbocation becomes more stable, what happens? Its energy lowers, which means the transition state energy lowers, and you get a faster reaction. If we worry about Hammond's postulate and all of that stuff. So what dictates SN1 is the stability of the carbocation. What dictates the reactivity in SN2? Steric hindrance. So the steric hindrance dictates the reactivity in SN2. What reacts the fastest? Primaries. And then secondaries, tertiaries don't undergo a reaction, an SN2 reaction because too sterically hindered. So in these two epoxide reactions that we've seen, they both, I'll grant you, they both have SN2 characteristics because of the backside attack. But what's dictating the fact that the alcohol is adding to carbon B? The stability of the C delta plus. So this has, in terms of the regioselectivity, in terms of which carbon to add to, it's driven by SN. It's like an SN1 reaction. It's driven by the stability. In the reaction with any negatively charged nucleophile, going back, any negatively charged nucleophile like R minus, C minus, Cl minus, Br minus, O minus. This one, because this is a strong nucleophile, and these two carbons, there's no positive one charge for them to share. So given that, this looks more like an SN2 reaction and is driven by sterics. So that's the ultimate difference between acid catalyzed or under acidic conditions and under strong nucleophile conditions. So when you add acid, where do you add the nucleophile? Most substituted carbon. When you have a strong negatively charged nucleophile, where does it add? The opposite, the least sterically hindered. First predictor, whether the carbon is primary, secondary, tertiary. Secondary predictor for SN2, steric hindrance. Ring, bigger than methyl group. Everybody with me? We'll find out. So then, so if I do this reaction under acidic conditions, wait, didn't I just ask this question like 10 minutes ago? It's pretty good that I put that together. So let me ask it again now. Where is the RO group going to end up, on A, B, or both? Shannon?
B, because it's the most substituted carbon.
Is it? B is what kind of carbon? A is... Okay. Now I'm doing this under acidic conditions, right? So if I protonate that oxygen, and it pushes the electron density down to A and B, which carbon is going to have the greatest positive charge? They both are going to have the same, they both would have the same positive charge. They're both secondary. Does it matter what's attached to a secondary carbocation? No. As long as it's secondary, we've treated them all with the same stability. So if this reaction is driven by an SN1-like mechanism where the ROH is going to add to the carbon with the greatest delta positive charge, and if both carbons have the same delta positive charge because they are both secondary, I'm going to get a 50-50 mixture of adding the OR group to A and B. Sterics only play a role in strong nucleophile opening the epoxides. Not when SN1 or when the greater delta positive charge is predicting the reaction. So I would get a 50-50 mixture of these two products. So we have two completely different sets of possible reactions. You can open up the epoxide with base or with a strong nucleophile. You can open it up under acidic conditions. Does that make sense? So in the homework problems with the Grignards, you're always going to add the Grignard to the carbon that's most accessible, least hindered, least substituted. And unfortunately, I can't change the set of conditions to do the reverse. Now I can change conditions. Let's say if I wanted to take my epoxide, and just for this, I'm just going to make that a CH2 so it's clear which one is more or less sterically hindered and which one's going to have more or less delta positive charge. But let's say I wanted to add an OR group to this epoxide, and I wanted to add the OR group to carbon A. I could use, H plus an alcohol to do that, because the H plus would protonate the oxygen, and then the ROH would attack carbon A, lose the H plus, and I've now added my OR to carbon A. If I wanted to add the OR group to carbon B, how would I do it? What? I need a different set of reagents. What?
Nucleophile?
So do what nucleophile for what?
Nucleophile, like,
But I want to add an OR group. So let's make the RO group a strong nucleophile. What's that? RO. Strong nucleophile. And we're back to the yin and the yang of organic chemistry. Our ability to do one thing and then do the opposite by changing the conditions. So if I wanted to add the OR group to A, I would do it under acidic conditions. If I wanted to add it to B, I would just use an alkoxide. And then H plus H2O. Right? So I can do either one. And so that's the importance of the epoxides. The specific reagents, really, you have to classify them. Do they have an acid or do they not? If they have an acid, nucleophiles can add the most substituted carbon. If they don't, nucleophiles can add to the least sterically hindered carbon. Is how it's going to work. Now, one thing that I didn't go over as a review was what are the two methods that you use to make epoxides out of alkenes. So I'll just leave this as a question for you to ponder. If I have this alkene, what two reagents or sets of reagents could I use to make the epoxide? Because in order to use an epoxide, I got to be able to make it. And then one of those methods is either stereoselective, regioselective, or stereospecific. So maybe we'll do that real quick at the beginning of class on Wednesday. Okay, for Wednesday, the video is up. It's oxidation of alcohols and I think some other things. There's no problems to do. No no written problems to do, so give you a chance to get caught up on some top hat, 3x5 cards, mass spec homework, whatever you've got. Right? And I know there's like some vicious rumor going around that they're going to cancel classes.